Hi, everybody. Welcome back to Intro to Physics, day somewhere towards the end. We have one last week together to hit a couple last topics, just very briefly skim through some of these. And then later on this week, we'll do a nice course review for you guys. If you have any lingering questions about anything, that will be a great chance to ask that. But that's the plan for Thursday, is to go through, kind of hit all of the topics that we talked about this summer, kind of what the key takeaways are from that, key equations to remember, that sort of thing. So look forward to that review on Thursday, which means we have today, tomorrow, and Wednesday to talk about gravitation and rotational motion. So gravitation is one of my favorite things to think about. I mean, I am an astrophysicist, so thinking about things pertaining to space just really excites me. So hopefully this is interesting to you guys, and we'll be taking some of our physics concepts and extending them out now into the universe, which, I mean, what more could you ask for? All right, so we're going to start off with these two quotes, which I think are very interesting to think about, kind of thought provoking. So the first one: we live in a changing universe, and few things are changing faster than our conception of it. So just thinking about like how vast the universe is just, it's mind blowing. Like it's crazy to think about how big the universe is. I mean, if you think about the Earth itself, like the Earth seems pretty big. I mean, there are billions of people on it, and there's still empty spaces. Um, so the Earth is pretty big, but in the grand scheme of things, like it's one of the smaller planets. Um, which these planets that we're thinking about are orbiting around our sun, which is pretty small compared to some of these other stars, which are spread super far apart from each other. And over the past a decade or so, we've come to learn about thousands of different planets orbiting around different stars, these exoplanets that we had no idea were out there until fairly recently in the grand scheme of things. So for a long time, people thought that these 9 planets, including Pluto at the time, were the only planets that existed. And now we know that that's not true. And so that discovery has really changed the way we view the universe. And it just seems like every couple of years there's another discovery in astronomy that just kind of changes the way that we perceive um, our world and our solar system and the universe that we live in. So I just think that's really kind of cool and exciting to think about. The second quote: pick a flower on Earth and you move the farthest star, is also really crazy to think about too. And that pertains to gravitation, which we've talked about before a little bit, acceleration due to gravity on Earth, and how anything that has mass has a force of gravity. So everything is attracting other things to itself. So when we pick a flower and move it somewhere else, that flower, since it has mass, has a force of gravity associated with it. And this force of gravity extends to every single object, right? We can't selectively gravitate towards something and ignore the gravitational stuff from other things. Like it it doesn't work like that. So when we pick a flower on Earth and we move it somewhere else, we've changed this gravitational field slightly, not a whole lot, but slightly. And so this effect kind of ripples out and affects everything else in the whole universe. Um, Slightly. I mean, not a whole lot, but still the fact that our gravitational fields here are in fact gravitationally interacting with the moon or things farther than that, I just think is really neat. Okay, so we're going to start with a little bit of historical context just to kind of build up this how our understanding of the universe came about, and our understanding, particularly of gravity, how that came about. So these people that I'm choosing throughout history are really key players in the kind of evolution of thinking about the solar system and the universe. Although there are definitely other astronomers who contributed to this changing perspective as well. Um, so this is just highlighting a couple of key people. So first of all, Aristotle, back in, well, he lived in 382 to 322 BC. Uh, the model of the universe that he thought to be correct was called the geocentric model of the universe. So if we take that geocentric word and we break it apart into its different components, right? We have geo and we have centric. So geo is the prefix pertaining to Earth, like geography, geology, all that jazz. So that's Earth, and then centric, meaning at the center. So his understanding of the universe was that the Earth is at the center, and everything else that he knew of orbited around the Earth. So he didn't know about all of the planets at that point, just the ones that you could see with your naked eye. So Mercury, Venus, Mars, Jupiter, and Saturn are ones that you can see with your naked eye if you're very observant and know where to look. So he thought that those planets and the sun and the moon and the stars orbited around the Earth in perfectly circular, unchanging orbits. And so there was this like sphere around the Earth of stars that were kind of fixed. They were all at a fixed distance, and some were brighter than others and dimmer than others, but that they were all at the same distance. And it was just this kind of like bubble of stars around us. And that seems like, from our perspective, that seems kind of ridiculous. Like, how can you believe that? Um, but I mean, if you think about it, it's kind of arrogant for us to say, like, oh my gosh, he's so idiotic for thinking that. Like, how could he possibly believe that? Because if you just stand out on the earth, looking up at the night sky, it does not feel like you are moving, right? It seems like, and if you look long enough, it seems like the sun, the moon, the stars, all of them are moving around you, and you are a stationary point, right? Since we're on the earth, we can't really feel it moving in the same way that, like, if you're driving in a car down a straight road at a constant speed, you don't really feel like you're moving, I don't know, 50 miles an hour. You feel like you're kind of just there. And like, if you look out the window, it looks like the world is rushing past you. So that was his perspective. And if we keep that in mind, it doesn't seem so crazy that he's come up with this particular model of the universe, right? That he is stationary on the earth and that everything else is what's moving around us. So a little bit later, Ptolemy in 100 to 170, he edited this geocentric model of the solar system, right? So he, observed the heavens, and he noticed that sometimes the planets would move forwards, and then they'd appear to go backwards, and then they'd appear to move forwards again in the sky. And they would do this, excuse me, kind of periodically. And so, you might have heard of like the retrograde motion of Mars, especially. Retrograde motion means that apparent backwards motion. And so he observed this in the planets, but not with the moon, not with the sun, not with stars. So he edited this geocentric model to include what are called epicycles, which mean that the planets do follow an orbit around the Earth, but as they follow the orbit, they're kind of spiraling around in their orbit. And so that spiral addition kind of accounts for that apparent forward and backward and forward motion. So that was his kind of addition to this understanding of the universe. Next up, many, many years later, so of course there were astronomers between these two people. But again, I'll just highlight some of the key things. So Copernicus in 1473 to 1543, he developed a heliocentric model. So helio is the prefix for sun, right? Helium was an element that was first discovered in the sun before it was discovered on Earth. And so that's why we named it helium, because we saw it in the sun, Helios. So heliocentric means that the sun is in the center of the solar system, and that everything else then is orbiting around the sun. And you can see in his diagram, he does still have the moon orbiting around Earth, Terra. Um, so this was really a revolutionary, lol, revolutionary concept at the time, that there could be something other than Earth at the center of the solar system, because that would mean that Earth is moving, and it doesn't feel like we're moving, right? And that would mean that we are not the center of the universe, which we don't like to admit all the time. So after him came Galileo in 1564 to 1642. And he really kind of destroyed the idea of a perfect geocentric universe, meaning like everything orbits around the Earth, because he used this telescope, that a model that he invented. He pointed it up in the sky. I mean, previously, navigators like sailors had had spy glasses and stuff that they used for navigation on Earth. But he pointed this telescope up at the sky, particularly at Jupiter, and noticed that Jupiter had moons that were orbiting around it, not around the Earth. These moons were orbiting around Jupiter. So he discovered four of those moons. You can see them there in the picture: Ganymede, Callisto, Europa, and Io. And so, therefore, there could not be a perfect geocentric universe. So that was really quite a discovery there. Um, So he was also the first one to discover that objects are pulled to the center of Earth. He didn't necessarily name the phrase gravity, but that's the concept that he was alluding to. Um, and then he also discovered that Venus has phases, kind of like the moon has phases, which were all really um, interesting things. Okay, this is one of one of the guys that I think is fascinating. People don't really know how to say his name. I was always taught it was Tycho Brahe. Some people call him Tycho. Some people say Brahe. I have no idea. So I'm just going to call him Tycho Brahe. So he lived from 1546 to 1601. And he was just this, I, he was crazy. I mean, in some ways, like a really good way, but in some aspects, just like, what are you doing with your life, Tico? Like, I don't understand. So, just for a little bit of insight into his life, when he was in college, he got into a duel with a fellow student about who was the better mathematician, and he ended up losing part of his nose in the duel. Like, it got cut off with a sword. And so he replaced the tip of his nose with um, a brass nose. And so that was like his look for the rest of his life, and was this like brass fake nose, because he thought he was the better mathematician. He had an elk for a pet, which is also kind of a strange thing. But he built his own observatory, which enabled him to make the most precise celestial observations like ever. And so that's what he was primarily. He was a data collector. He didn't necessarily know what to do with the data. He didn't analyze it and find patterns, that sort of thing. He hired other people to do that. But he took all of the data and he hoarded that research. He wouldn't really let other people see it, except for the little portions that he was willing to share. And so his model of the universe is kind of a hybrid of of the two models that we've seen so far. So it doesn't really have a name other than the Tychonic system. But basically, what he said was that the sun is at the center. Well, kind of. So the moon and the sun orbit around the Earth, but the rest of the planets orbit around the sun, which is orbiting around the Earth. So I guess you can't really say like one of them is at the center, but it's awkward. But that was his kind of compromise between, the historical geocentric model and this revolutionary concept of the heliocentric model. Um, that's what he came up with. And so now he had hired this apprentice to work for him called Johannes Kepler. And Kepler was just this brilliant theoretical physicist. He was great at analyzing data and finding patterns and condensing those patterns into laws, which we'll learn about in just a little bit. Um, but Tycho Brahe kept Kepler working on this data that was just not interesting to Kepler. He really wanted to figure out what was going on with Mars, and Brahe would not give him the Mars data. And so the circumstances surrounding his death, Tycho Brahe's death, are actually very kind of mysterious. And actually, several groups of scientists have like exhumed his body and tried to figure out the cause of death. So over the years, it's been kind of up in the air as to what caused him to die. But Tycho Brahe was like a noble, so he was a really important person, invited to a lot of important events. And one theory surrounding his death is that he was invited to a party by some like really prestigious people, and it's very impolite at the time to leave the table before your hosts do. So he had drunk a little too much, probably wine, um, and really needed to use the bathroom. But he did not want to be like socially unacceptable by leaving the table before his hosts. And so he just held in his pee so long that his bladder exploded, or he got like a severe kidney infection, just because he didn't want to be rude. So that's one. That was one theory about his death. The other was that his nose eventually poisoned him because it was a brass nose. Brass isn't really something that you're supposed to have like in your body for an extended period of time. Um, they found traces of mercury and arsenic in his beard, so they thought that maybe somebody had poisoned him, possibly Kepler, to get his data. That was a theory. Um, yeah, just just lots of different theories about his death. Now scientists think that it was three causes: obesity, alcoholism, and oh, I forget the other cause, but it was some other like normalish sounding thing. But still, I just think that ambiguity was a little interesting. Anyway, here's his assistant, Johannes Kepler. So he inherited slash stole slash murdered his boss for all of his data. But anyway, he used Brahe's data to create three very important laws about the motion of the planets. And so since he had access to the best data that was available at the time, his understanding of the universe was very different than the others. In You can see in this picture. So it is a heliocentric model of sorts. You can see the sun is not at the center because we no longer have circular orbits. Now the orbits of planets are ellipses, or kind of stretched out ovals. Um, and they're still going around the sun, but now the sun is not at the very center. It's off at what is called a focus of the ellipse. Um, and so stretching out these orbits into ellipses instead of having them as circular orbits solved the problem of that apparent backward motion of the planets, right? That retrograde motion. So we didn't need epicycles anymore. And there's kind of a rule in science that the simplest solution is probably the right one. So if you're like just thinking through a problem and you have to do all these crazy complicated things to make your answer work out, it's probably not the right answer just because nature doesn't really work like that according to our observations. So the fact that he was able to take out epicycles and simplify this understanding of how the planets move, um, that was great. That was progress. After him came Isaac Newton. Of course, we have already heard about him quite a bit. Um, so he took remember, Galileo's the one who theorized that, everything falls to the center of Earth. So he came up with gravity. Isaac Newton did not, although he is credited for discovering gravity. Remember that, like, apple falling on his head? Oh, gravity, that whole thing. He didn't really discover gravity because Galileo theorized on it hundreds of years before he did. He just expanded on Galileo's idea, put a term to it, and discovered that it's universal. So gravity is not just present on Earth. It doesn't just cause things to fall to the center of Earth when you're close to it. Gravity is everywhere in the universe, and it affects everything in the universe. So that was really what progress he made with this understanding of gravity. And he's the one that said, well, if gravity is universal, then maybe it's gravity that's causing the motion of the planets. And we'll get into that a little bit more now. So he, the story goes, that he was sitting under this tree and looking at the moon, and an apple fell onto his head. And he said, oh, maybe the moon is falling the same way that this apple is falling. Um, but instead of falling straight towards the earth, it falls around the earth. Right? And it's kind of a strange way to think about it, but it makes sense because if the moon didn't fall, then it would follow a straight line path and just it'd be gone. But because it's attracted to the earth, it falls along a curved path around the earth. So you can think about like trying to throw a rock as far as you can, right? So if you're standing on top of a really, really, really tall building, and you're throwing a rock, right? If you throw it sort of hard, then it'll follow that projectile motion parabola that we talked about a couple weeks ago. If you throw it a little bit harder, it'll go a little bit farther before it hits the ground. If you throw a little harder, it'll go a little farther, etc. Well, at some point, if you throw it at a certain speed, it will fall down, but it will completely miss the edge of the earth. And it will just keep falling and falling and falling, trying to hit the edge of the earth, but it keeps missing the earth, until it eventually comes back and like hits you in the back of the head or something, until it's completed an orbit. So if you can find that particular velocity to throw that rock at, then you will be able to put it into orbit. Right? So a little speed, parabolic path hits the ground. More speed, parabolic path hits the ground. Highest speed, parabolic path misses the ground, goes into orbit. So that was his idea, his understanding of what is happening with the moon, right? It's going at that particular speed to be trying to fall to the earth just like the apple does, but it just is missing because it's going has this horizontal component to its velocity that keeps it from crashing into the earth. Right? And so if that's the motion that the moon makes, then maybe these planets have that same motion around the sun, right? We are falling towards the sun. We just keep missing it and are in this orbit around the sun. So we don't crash into the sun because we have enough tangential, or you remember the part of the curve that's tangent to the curve is the part that's just touching it at one point. So we have enough tangential velocity to stop us from hitting the sun. Right? And so what would happen if the tangential velocity was 0. Well, if we had no tangential velocity, no kind of sideways velocity in this top picture, then we would fall straight into the sun, right? If there was no gravitational force, so no attraction holding us into the sun, then we would just fly out in that tangent direction forever. We wouldn't be in an orbit. So there's this balance that has to happen between the tangential velocity and the gravitational force in order to keep us in an orbit. Right? And that balance looks different for different things. That's why we get different shapes of orbits. Okay, so both a rock that you throw and the moon and the planets have both that velocity that carries them sideways, tangential velocity. Okay. So now we're going to revisit some of Newton's laws, right? Because he created these laws of motion that we learned about a couple of weeks ago. And now he's creating this, sometimes I call it the fourth law, Newton's fourth law, which is gravitation. So now we can kind of tie these things together, right? So he incorporated inertia into his first law of motion. Without an outside force, moving objects keep moving at a constant speed in a straight line. That's his first law of motion. That's inertia, right? There has to be some unbalanced force to change the motion of an object. So if it changes its speed or direction, if it changes its motion, that's because there was some outside force acting on it. So when we think about the moon, it doesn't follow a straight line path. It orbits around the Earth, so there has to be some outside force acting on it, right? So also reviewing, I don't know, the second week of class, the three types of acceleration or changes in motion. You can speed up, you can slow down, or you can change direction. Now, if something is in orbit, it is constantly changing the direction that it is moving. So circular motion, orbital motion, is constantly changing direction, which means it is accelerating. And Newton's second law tells us that if there's an acceleration, then there is a net force, right? F equals ma. Acceleration implies a net force or an unbalanced force. So if it's moving in a circular motion, there has to be an unbalanced force again, right? What is that force? Well, that was the question he was trying to answer, and he answered it with gravity, right? Just the same as an apple falls down to Earth, same reason the moon is orbiting around the Earth. It's just gravity. So previously we've talked about the force of gravity as this equation, right? Force of gravity equals mass times the acceleration due to gravity. Well, that's all well and good if you're close to the Earth, right? Remember we said that G is kind of approximately 9.8 meters per second squared, but that's an average, right? It's slightly different for different locations on Earth. Well, when we're not close to the Earth, when we're close to something else or any gravitating body, that equation changes a little bit. So now the force of gravity equals capital G times mass 1, so mass of the first object, times the mass of the second object, divided by the distance between their centers squared. And it acts towards the bigger gravitating body. So this is our new equation for gravity, and this is what's called Newton's law of universal gravitation, this equation here. So since we're dealing with a force, direction is important. Right? Again, it's towards the gravitating body, the larger gravitating body, the more massive, I should say, the more massive gravitating body. This capital G in the equation is a constant known as Newton's gravitational constant. Usually we just call it big G, which sounds kind of like a gangster name. I don't know. Maybe that's just me. But anyway, big G is 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. So this constant doesn't seem very large. And times 10 to the negative 11, it's not very large, but it is important. Um, these two masses, again, are the masses of each object, because in order to have gravity affecting something, you need to have the gravitating object and the thing that it's affecting, right? And those are always going to be in kilograms. Sometimes you'll see this equation written as capital M and lowercase m if the two masses are extremely different, like for the Earth and the moon, or Mars and the sun. They have very different masses. So sometimes it'll be capital M for the larger mass and little m for the smaller mass. And then again, r is the distance between their centers in meters. Now you need these units to be these specific units, right? We can't use distance in centimeters because then our unit for this constant will not be consistent. So we need mass in kilograms, we need distance in meters in order to use this gravitational constant. Okay, so gravity on the moon by the Earth is the same as the force of gravity on the Earth by the moon. Right? It's just a different direction, Newton's third law. Same magnitude, opposite direction. And that's the same for any particular pair of objects. The force of gravity of my computer pulling on me is the same magnitude as me pulling on my computer, just opposite directions, right? It doesn't really matter what you choose as mass 1 and what you choose as mass 2 because we're multiplying them together. So it doesn't really matter. The standard though is to use the bigger mass as mass 1 and the smaller mass as mass 2. Okay. So the force of gravity is actually an incredibly weak force compared to some of these other forces um, that you'll learn about, maybe in physics 1, definitely in physics 2, things like the electrostatic force, right? Very large compared to the force of gravity. If you take a balloon, well, maybe not in Florida. Florida is pretty humid. But if you take a balloon and you rub it on your head, you can like stick it on a wall and it will stay there. Same thing, take a magnet, stick it on a fridge, it will stay there. Magnetism and electricity, those forces are much stronger than the force of gravity. So the balloon will tend to stick to the wall, again, if it's not too humid, um, because that electrostatic attraction between the wall and the balloon is much stronger than the force of gravity pulling down on that balloon. Same thing with the magnet. That magnetism force is stronger than the gravitational attraction. So the force of gravity seems like the most significant force in our life because it keeps us grounded, like on the earth. That's kind of important. But really, in the grand scheme of forces, it's actually pretty small. Okay, so I want you to take a look at this equation. Just really quickly think through this. Sedna is 3 times farther from the sun than Eris. These are both um, dwarf planets. So assuming Sedna and Eris have the same mass, compare how much gravitational force each gets from the sun. Okay, so take a quick minute, think through how you might set up this problem using that Newton's law of universal gravitation equation, and then we'll come back together in 30 seconds and talk about it.